In the crash course, we will learn a few foundational key concepts. None are more important than exponential growth. Understanding this will greatly enhance our chances to form a better future. Here's a classic chart displaying exponential growth, a chart pattern that is often called a hockey stick. We are charting an amount of something over time. The only requirement for a graph to end up looking like this is that the thing being measured grows by some percentage over each increment of time. The slower the percentage rate of growth, the greater the length of time we'd need to chart in order to visually see this hockey stick shape. Another thing I want you to take away from this chart is that once an exponential function turns the corner, even though the percentage rate of growth might remain constant and possibly quite low, the amounts do not. They pile up faster and faster. In this particular case, you are looking at a chart of something that historically grew at less than 1% per year. It is world population, and because it is only growing at roughly 1% per year, we need to look at several thousands of years to detect this hockey stick shape. The green is history, and the red is the most recent UN projection of population growth for just the next 42 years. Certainly by now, math-minded folks might be getting a little uncomfortable because they might feel I'm not presenting this information in a classical or even very accurate way. Where mathematicians have been trained to define exponential growth in terms of the rate of change, we are going to focus on the amount of change. Both are valid, it's just that one way is easier to express as a formula, and the other way is easier for most people to intuitively grasp. Unlike the rate of change, the amount of change is not constant. It grows larger and larger with every passing unit of time, and that's why it's more important for us to appreciate than the rate. This is such an important concept that I will dedicate the next chapter to illustrating it. Also, mathematicians would say that there's no turn the corner stage of an exponential chart, because this is just an artifact of where we draw the left-hand scale. That is, an exponential chart can nearly always look like a hockey stick at every moment in time, as long as we adjust the left axis properly. But if we know the limits, or boundaries, of what we are measuring, then we can fix the left axis, and the turn the corner stage is absolutely real and vitally important. For example, the total carrying capacity of the Earth for humans is thought to be somewhere in this zone, give or take a few billion. Because of this, the turn the corner stage is very real and not an artifact of graphical trickery. The critical takeaway for exponential functions, the one thing I want you to recall, relates to the concept of speeding up. You can think of the key feature of exponential growth either as the amount that is added growing larger over each additional unit of time, or you can think of it as the time shrinking between each additional unit of amount added. Either way, the theme is speeding up. To illustrate this using population, if we started with 1 million people and set the growth rate to a measly 1% per year, we'd find that it would take 694 years before we achieved 1 billion people. But we'd be at 2 billion people after only 100 more years, while a third billion would require just 41 more years. Then 29 years, then 22, and then finally only 18 years to add another to bring us to 6 billion people. That is, each additional billion people took a shorter and shorter amount of time to achieve. Here we can see the theme of speeding up. This next chart is of oil consumption, perhaps the most important resource of them all, which has been growing at the much faster rate of nearly 3% per year, so we can detect the hockey stick shape over the course of just 150 years. And here too, we can fix the left axis with some precision because we know with reasonable accuracy how much oil the world can maximally produce. So again, having turned the corner is an extremely relevant and important event to us. And here's the US money supply, which has been compounding at incredible rates ranging between 5 and 18% per year. So this chart only needs to be a few decades long to see this hockey stick effect. And here's worldwide water use, species extinction, fisheries exploited, and forest cover lost. Each one of these is a finite resource, as are many other critical resources, and quite a few are approaching their limits. And here is the world you live in. If it seems like the pace of change is speeding up, well, that's because it is. You happen to live at a time when humans will finally have to confront the fact that our exponential money system and resource use will encounter hard physical limits. And behind all of this, driving every bit of every graph, is the number of people on the surface of the planet. Taken one at a time, any one of these charts could command the full attention of every earnest person on the face of the planet. But we need to understand that they are, in fact, all related and interconnected. They are all compound graphs, and they are all being driven by compounding forces. To try and solve one, you'd need to understand how it relates to the other ones that you see, as well as others not displayed here, because they all intersect and overlap. The fact that you live here, in the presence of multiple exponential graphs relating to everything from money to population to species extinction, has powerful implications for your life and the lives of those who will follow you. It deserves your very highest attention. Let's move on to an example that will help you better understand these graphs. Please join me for Chapter 4, Compounding's the Problem. Thank you for listening. The purpose of this mini presentation is to help you understand the power of compounding. If something, such as a population, oil demand, a money supply, anything, steadily increases in size as a proportion of its current size, you get a graph that looks like this. A hockey stick. Said more simply, if something is increasing over time on a percentage basis, it's growing exponentially. Using an example drawn from a magnificent paper by Dr. Albert Bartlett, let me illustrate the power of compounding to you. Suppose I had a magic eyedropper and I placed a single drop of water in the middle of your left hand. The magic part is that this drop of water is going to double in size every minute. At first, nothing seems to be happening, but by the end of a minute, that tiny drop is now the size of 2 tiny drops. After another minute, you now have a little pool of water that is slightly smaller in diameter than a dime sitting in your hand. After 6 minutes, you now have a blob of water that would just fill a thimble. Now, suppose we take our magic eyedropper to Fenway Park, and right at 12 o'clock in the afternoon, we place a magic drop way down there on the pitcher's mound. To make this really interesting, suppose that the park is watertight and that you are handcuffed to one of the very highest bleacher seats. My question to you is this: how long do you have to escape from the handcuffs? Days? Weeks? Months? Years? How long would that take? I'll give you a few seconds to think about it. The answer is you have until 12:49 on that same day to figure out how you're going to get out of those handcuffs. In less than 50 minutes, our modest little drop of water has managed to completely fill Fenway Park. Now let me ask you this. At what time of the day would Fenway Park still be 93% empty space? And how many of you would realize the severity of your predicament? Any guesses? The answer is 12:44. If you were squirming in your bleacher seat, waiting for help to arrive, by the time the field is covered with less than 5 feet of water, you would now have less than 5 minutes left to get free. And that right there illustrates one of the key features of compound growth. The one thing that I want you to take away from all of this: with exponential functions, the action really only heats up in the last few moments. We sat in our seat for 44 minutes, nothing much seemed to be happening, and then in 5 minutes, bang, the whole place was full. This example is loosely based on a wonderful paper by Dr. Albert Bartlett that clearly and cleanly describes this process of compounding, which you can find in our essential reading section. Dr. Bartlett said, "The greatest shortcoming of the human race is the inability to understand the exponential function." And he's absolutely right. With this understanding, you'll begin to understand the urgency I feel. There's simply not a lot of maneuvering room once you hop on the vertical portion of a compound graph. Time gets short. This makes compounding the first key concept of the crash course. Now, what does all of this have to do with money and the economy and your future? Haha, I can't wait to tell you. Let's go find out.